Hi class, this lecture continues in section 1.2, and here what we want to do is we want to talk about continuity. And so the first definition, or the only definition we're going to have for this, is about a function being continuous at a point. So a function f is continuous at the value x is equal to a if you have the following three conditions. One, when you plug a into the function, it exists. Okay, so there's an output at a. The limit as x goes to a of the function exists. Okay, so the limit's not undefined. And three, the limit as x goes to a of f of x is actually just equal to f of a. Okay, so the limit is the same as the output. Okay, that's what it means to be continuous at a point. So a function is continuous over an interval if it is continuous at every point in that interval I. Okay, if f is not continuous at x is equal to a, then we say f is discontinuous, or that it has discontinuity at x is equal to a. All right, so what I want to do in this lecture is just walk you through three examples asking if the function is continuous at a specific x value. Okay, and remember you have to meet all three of these conditions. Okay, so the first one, this is the function f given by, so we have this function f of x is equal to x squared minus 5, continuous at x is equal to 3. So why or why not? Well, it needs to meet all three of these conditions, okay? So the first one, does f of 3 exist? Yes. So just f of 3 here is just equal to 3 squared minus 5, which is 9 minus 5, which is 4. 2, the second thing, the limit as x goes to a has to exist. Yeah. If you look, the limit as x goes to 3 of x squared minus 5, well, you know, this is a polynomial function, you can just plug it in. So this is 9 minus 5, which is 4. So yes. And then finally, the third condition, we see that the limit as x goes to 3 of f of x is just equal to f of 3, which is just equal to 4. Okay, so you know what? This function is continuous. It is continuous at x is equal to 3. So we're good. All right, let's go and maybe see some examples of where it's not continuous. Okay, so we've got this one here, right? Is this function, so we've got a piecewise function g of x here. Okay, it's equal to 1/2 x plus 3 when x is less than -2, and it's equal to x minus 1 when x is greater than or equal to -2. All right, so is it continuous at x is equal to -2? All right, well, you got to go through the three components. The first one here is, does g of -2 exist? Yes, it does. G of -2, well, when x is equal to -2, you'd use this formula right here. So it's just equal to -3. All right. The second one, does the limit as x goes to -2 of this function g of x exist? So that's a little bit tricky, right? So you got a piecewise defined function. So what you got to do is you got to look at the one-sided limits. So the limit as x goes to -2 from below of g of x. Well, for that, you'd actually use this right here. You'd say, okay, as you're going from -2 from below, you're going to use this equation right here. So all you're going to do is you're going to take -2 and you're going to plug it into this equation. So you get 1/2 times -2 plus 3. Okay, that's equal to 1/2 times -2 is -1 plus 3 gets you 2. And then you got to look at the limit as x goes to -2 from above of g of x. Well, from above, you're going to use this function because your value is greater than -2. So you're going to take -2 minus 1, you get -3. So the one-sided limits don't agree. So no, the limit does not exist. Okay, so since right here, since you immediately know that the limit does not exist, you can just say it is not continuous. At x is equal to -2. Okay, there's a point of discontinuity. All right, let's do one last one here. So let's take this function. Is the following function continuous at x is equal to 3? So it's one that we've been working with, okay? Although here it's just h of x, and it's kind of defined as a piecewise here. So it's equal to x squared minus 9 divided by x minus 3 when x is not equal to 3. And when x is equal to 3, it's equal to 7. Okay, so first off here, 1, does h of 3 exist? Sure does, yes. H of 3, when x is equal to 3, you're just going to use this value here, it's equal to 7. Does the limit as x goes to 3 of h of x exist? Actually, it does. So remember that this right here ends up just looking like x plus 3. So this graph is going to look something like this. When you get x equals 3, it's going to be a hole, and this hole is going to look like it's at 6, but then at the number 7, the graph is redefined with this dot right here. So it looks like the limits as x goes to 3 of this graph is going to be equal to 6. Okay, so so it's like, all right, well, great. H of 3 exists, and the limit as x goes to 3 exists. But what we see, the limit as x goes to 3 of h of x is not equal to h of 3. Okay, so we needed to have, like we did here, that the limit is equal to just plugging it in, which is not the case here. So the function is not continuous. At x is equal to 3 because the limit as x goes to 3 of h of x is not equal to h of 3. Right, because the limit is equal to 6, but h of 3 is equal to 7. All right, class, I hope this little video on continuity and these examples were helpful.